Hi everyone! Today we are going to plan my next summer vacations on the Atlantic coast using the stable model semantics of logic programs. Thing is, many of my friends are logicians, and we like our schedules well-founded and properly justified. So let's dive in and write a little program to schedule our activities. First, we expect a lot of sun. Of course, if it is sunny, then we go to the beach. Once at the beach, if we have a beach ball, then we play beach volley, and that's amazing. Another option is to organize a picnic if we have food at the beach. If we play and it's sunny, then we'll make sure to drink a lot of water. Oh, and guess what? I just bought a beach ball for the occasion. Okay, let's rewrite this into a more formal way, and here is a nice logic program. I would even say that this is a positive logic program. Nothing to do with the nice vacation perspective. A logic program is just a set of rules, each made of a body, which we should think of as a conjunction of atoms, and of an head atom. Here it is positive simply because there is no negation symbol. Let's send this program to the others and see what they think about it. Matti answered me, and he sent the following model. Well, it sure is a model of my program under the classical semantics of propositional logic, but I really don't know how he plans to have a picnic without food. A more reasonable approach would be to only apply a rule if its body is satisfied, right? Let's do this until no rules apply anymore. There it is. This is called the minimal model of our positive logic program. It is not hard to see that it is unique, mainly because the order in which rules are applied does not matter. Notice that every element of my model is there for a good reason. It has been obtained by applying a rule at some point. Typically, no more picnic, since we have no food, thus we do not apply the picnic rule. This model makes much more sense. Matti again. He is now concerned about tea time and proposes some other program to decide this. Let's take a look. So if we're not drinking tea, then we should drink coffee. If we're not drinking coffee, on the other hand, then we should drink tea. Drinking tea implies getting a cookie, that's cool, and drinking coffee without getting a cookie makes you sad, I can imagine, yeah. Wait. This is no longer a positive logic program. It is a regular logic program, meaning the body can feature some negated atoms. Interesting. Let me evaluate this new program using my previous method, applying rules until we cannot apply rules anymore. Matti is doing the same on his side, but wait, we don't obtain the same result? I see. We did not apply the rule in the same order, which does matter now that our logic program is no longer positive. It's even worse, actually. If we start applying this rule, then we can further deduce things that would have prevented the application of the first rule. That's super counterintuitive. Let's manipulate a little bit the notion so that the order of the rules does not matter anymore. Also, keep in mind that we would like everything in a model to be justified, meaning it has to be obtained from a rule at some point. Therefore, there might be several possible results. We cannot have both tea and coffee, since to justify one, we need to exclude the other. So there are probably two models, one with coffee, one with tea. Okay, let's say I have a candidate interpretation, here tea and cookie, and I would like to know whether I can indeed deduce it. Surely, the rules whose body negates an atom of my candidate interpretation should not be used. So let's get rid of those. Also, we can get rid of negations in the other rules, because we aim to deduce tea and cookie, and nothing more. So if those negations are violated, it means we deduce too much anyway. This simpler program that we obtain is called the reduct of our logic program with respect to the candidate interpretation. Now, this reduct is a positive logic program, so it has a unique minimal model. Let's see whether our candidate interpretation coincides with this minimal model. Well, yes it does. The minimal model of the reduct for tea and cookie is tea and cookie itself. In this case, we say that tea and cookie is a stable model of our logic program. Let's take a look at another example. What about tea and coffee? So again, let's first get rid of rules and negations that should not be applied to deduce tea and coffee. Here is the reduct, let's see its minimal model now. And there it is. It is not the same as our starting interpretation tea and coffee. So tea and coffee is not a stable model. It all makes sense. We now have a nice notion at hand. An interpretation I is a stable model of a program P if it is a minimal model of the reduct of P with respect to I. Note that every stable model is a classical model of the program under the usual propositional semantics. So now, if we want to find all stable models of a program, we can simply look at all the possible classical interpretations. Let's try it. We get every possible reduct. Then we compute their respective minimal model. And finally, we compare with the starting interpretations. Well, in our example, it turns out there are only two stable models, tea and cookie, that we already identified, but also coffee and sad. As a side note, let's mention that stable models are often called answer sets, which is why we use the acronym AS down there. Okay, but this is a terrible way of finding stable models, right? If we have n atoms, then we might need to test 2 to the n interpretations to know whether there even exists a stable model. Well, we can of course guess a stable model, provided it exists, and then easily check whether it is indeed stable. As we have seen, this checking step is easy. It suffices to compute the reduct and its minimal model. This means that satisfiability under the stable model semantics is in the complexity class NP. But is it also NP hard? Maybe we can easily argue that it is the same as satisfiability under the classical semantics. Let's see. Well, surely, if there exists a stable model, then there exists a classical model, because every stable model is a classical model. The converse, however, is not true. Let's look at this very simple counterexample. If not A, then A. Under classical semantics, the singleton A is a model of this program. However, this is not a stable model, because you cannot use the absence of A to justify the presence of A. More formally, the reduct of this program with respect to A is the empty program, whose minimal model is therefore also empty, and thus different from the singleton A. So we need another way of showing NP hardness. Let's encode the three-colorability problem. That is, the problem of deciding whether we can color the vertices of a given graph with 3 colors, such that no adjacent vertices have the same color. This is a well-known NP-complete problem. So let's take a graph, say this one here. We would like to somehow encode it into a logic program. Let's introduce one rule per vertex like this, and let's do the same for each edge like this. Okay, it looks quite different from the previous logic programs we encountered, but you can really think of each of these facts as a propositional atom. Alright, so we encoded our graph. Now we need to somehow force each vertex to choose a color among, say, red, green, and blue. Do you remember the tea and coffee example? We were able to have stable models in which one either drinks tea or coffee, but not both. So we managed to express this kind of choices. Let's do the same here. Take a vertex phi and say that if it isn't green nor blue, then it must be red. Same with the other cases. And there it is. This vertex phi has to be either red, green, or blue. Finally, we need to guarantee that adjacent vertices have different colors. So take any two vertices u and v, and let's say that if there is an edge connecting those and they have the same color, here red, then this is a contradiction. Wait. How is nothing in the head of a rule a contradiction? Is that even a proper rule? Well, I'm slightly cheating here. If a rule has no head, we say that applying it yields a contradiction. We could easily do this in a proper way. Do you remember these rules we've seen before and which doesn't have a stable model? Well, we can incorporate it in our edge coloring rule, like this. And now you can check for yourself that if this rule is applied, then it cannot lead to a stable model. Alright, with all these rules at hand, one can verify that our starting graph is three-colorable if and only if this logic program admits a stable model. This proves that satisfiability under the stable model semantics is NP-hard, and thus NP-complete since we already know that it is in NP. Oh, one last thing about this reduction. If you look into the literature, you might see it presented like this with those variable symbols x and y. Using variables in logic programs is just a shorthand for the set of rules that you would obtain by considering every possible replacement of the variables by every possible term, just like this here. It is called the grounding step and allows to reduce to the propositional case. Let's take a small pause here and recap what we found out. First, my vacation plans appears much more complicated than expected. More seriously, we defined the notion of stable models of a logic program. Remember, an interpretation is a stable model of a program if it is the minimal model of the program's result with respect to that interpretation. We mentioned that every stable model is a model under the classical semantics, but that the converse may not be true, and that the satisfiability problems under these two semantics does not even coincide. We then proved that satisfiability under the stable model semantics is NP-complete, as we can reduce the three-colorability problem. Oh, wait, did I just forget to tell you about one of the most important properties of the stable model semantics? It's non-monotonic. This means that when you gain new knowledge by adding more rules, you may not be able to keep the same conclusion. Take a look at this small program here, with those stable models. Notice that in every stable model, we have this atom A, so we know that A holds for sure regardless of the specific stable model. But now, if I add this new rule, the stable models become those. And clearly A is not for sure anymore. This is non-monotonicity. Gaining knowledge does not necessarily extend the set of conclusions you can draw out of it. If you think about it, the classical semantics is, on the other hand, monotonic. Okay, I think we are done here. Matti again. Oh no, he modified the tea and coffee program. He claims it simplifies the program, but he made sure that the starting program and this new one have the same stable models. That is, their equivalence. Let's check. Yeah, it works. Those are indeed equivalent logic programs. But wait, I just bought plenty of cookies so that everyone can have some. Let's add this simple fact. With the original program, we can eradicate sadness with cookies. Oh, but in the modified program, we cannot. That's because Matti oversimplified the program. What we would need here is not only equivalence, but strong equivalence. Precisely, two logic programs P1 and P2 are strongly equivalent if for every other logic program R, the programs obtained by adding R to P1 and by adding R to P2 have the same stable models. This is clearly stronger than simple equivalence, right? Because with R being the empty program, we already guarantee equivalence of P1 and P2. But how do we decide whether two logic programs are strongly equivalent? I don't want to check every logic program R, there are infinitely many of those. Let's see how it is done under classical semantics, maybe it helps. Strong equivalence and equivalence happen to be the same under the classical semantics. It's not helping us. We know from the tea and coffee example that with stable model semantics, there are equivalent programs that are not strongly equivalent. Okay, so what can go wrong with my two programs when adding another program R to them? Maybe some classical model of P1 might become a stable model of P1 and R, but maybe not of P2 and R. This will always happen if a classical model of P1 was just lacking some justifications to be stable. Then by adding R to give all those justifications, we can always promote a classical model of P1 into a stable model of P1 and R. So, first condition for two programs to be strongly equivalent under the stable model semantics. They must have the same classical models, as otherwise we could differentiate them using this trick. For the second condition, you will have to take my word for it. For every classical model of the program, we take the corresponding reduct and then consider all the classical models of this reduct. The two programs are strongly equivalent if and only if those two tables here are exactly the same. Alright, this should help coordinate with the others. If you want to simplify the program for our vacations, please make sure it is strongly equivalent with the original one so that if we want to add more activities, it won't cause any trouble. Okay, real conclusion this time. We have explored stable models of logic programs, which are also called the answer sets of a program. We have seen that detecting whether a program admits a stable model is NP-complete, and that reasoning under the stable model semantics is non-monotonic. We also discussed strong equivalence under the stable model semantics and described a way to check whether two logic programs are strongly equivalent, by constructing for each program a table of classical models. By the way, this table exactly describes another semantics called the here and there semantics. But this is a story for another time, as I really have to go and buy some sunscreen for next summer. See you next time, bye!